Remember that childhood fascination of watching bubbles rise in a glass of soda? Did you know bubble sort is named after that same mesmerizing process? Let me show you how bubble sort works and how it's connected to these rising bubbles. Let's say we have a bunch of numbers in front of us. Now our job is to get these numbers sorted. Now both you and I know at first glance that these are the numbers from 1 to 7 jumbled up. And if it were up to us, we'd simply take out a pencil and a paper and write 1, 2, 3, 4, 5, 6, 7. Big deal, right? So if you and I know, the CPU knows too, right? That these are the numbers from 1 to 7 jumbled up? No. It turns out that microprocessors are actually pretty dumb. Now don't get me wrong, they're pretty darn fast, but they aren't too smart to realize what you and I can simply observe. If we want a CPU to sort numbers for us, we have to teach it to do so. And this is where bubble sort comes into the picture. It's just one of the many ways to teach CPUs to sort numbers for us. At the bare bones level, CPUs can only compare two numbers at a time and tell us which one is bigger or smaller. And additionally, they also know how to read and write to memory locations. It is these two abilities that bubble sort uses to teach CPUs how to sort these numbers. Now I'm going to explain to you step by step how we teach the computer to sort numbers based on these two abilities. The first step is to place these numbers in memory locations within a hard drive or SSD right next to one another, like the compartments of a train. We do this so that the CPU can access them easily. Let's assume that the numbers in front of us are stored somewhere in the memory right next to one another. Remember we discussed that a CPU only knows how to compare two numbers at a time? These two blue arrows you see on the first two numbers represent which two numbers will be compared at a time. So we start the process by comparing the very first two numbers. We check whether the first number is greater than the one after it. If it is, we ask the CPU to swap the two numbers. So what if the first number is not greater than the second? Then we ask the CPU to keep the numbers as it is. We will see this happen in a while. Is 7 greater than 1? Yes. So we will ask the CPU to write the number 7 into the second location and the number 1 into the first location. The CPU does this with its ability to read and write to locations like we discussed before. So let's begin the swapping process by writing 7 into the second location. Did you notice what happened? When the CPU tried to write the number 7 into the second location, we permanently lost the number 1. So we cannot directly write the number 7 into the second position. Otherwise, we will lose our numbers. Instead, before writing number 7 to the second position, we can ask the CPU to copy the value of the number in the second location into some random temporary location somewhere in our memory. Then once we are done copying number 7 into the second location, we can then copy the number 1 from that same temporary random location into position 1. This way we won't lose any number. The next step is to shift both the arrows by one position to the right. Again, we ask the CPU whether the left number is greater than the right number or not. Is 7 greater than 5? Yes, so again we ask the CPU to interchange the positions of both the numbers. After the swapping is done, we again shift the arrows by one position to the right. You may now notice a repeating process. We are comparing two numbers at a time, checking whether the left is greater than the right. If it is, then we swap the two numbers. If it is not, then we leave it as it is. This is what bubble sort is made up of. So now you may ask, why do we swap the two numbers if the left is greater than the right? Because we're trying to get the smaller numbers in the front and the bigger numbers at the end. And since CPUs can only compare two numbers at a time, we are constantly comparing two numbers from the very left memory location to the very right memory location. Now let's continue the process until the two arrows reach the end. So what happens when the two arrows reach the end? Or in other words, what happens when we are finished comparing the last two numbers in our sequence of numbers? Clearly, the sequence of numbers has not been sorted. So what should we do now? We simply ask the CPU to take the two blue arrows from the end to the very beginning and start the comparison process again. When the CPU finishes comparing two numbers at a time from the very first two numbers to the very last two numbers, we call that a pass. So let us make some observations of what has happened by replaying pass 1. Do you notice how the number 7, which is the largest number in the sequence of numbers, and which was placed at the very beginning of the sequence, gently moves and automatically drags to the very last position? Also notice 7 is already where it needs to be, that is, at the very end of the sequence of numbers, right after pass 1. This is why bubble sort is called bubble sort, because in each pass, the nth largest element automatically moves from wherever it was to where it should be at the end of the array. The process of this happening resembles the rising bubbles in a glass of soda that we saw in the introduction of the video. So, as discussed before, the comparison process of comparing two numbers at a time starts all over again from the first two numbers. So far, we have not discussed a situation where the left number is not greater than the right number. Is 1 greater than 5? No. So we will ask the CPU to do absolutely nothing and move on to the very next two numbers. Logically speaking, the reason we did not swap the numbers is because the smaller of the two is already where it should be, that is, in the front. We continue the same process as we did in the previous pass until we reach the very last two numbers. Now, during pass 2, there is no need for us to compare the last two numbers, that is 6 and 7, because as we discussed before, at the end of pass 1, we already got our largest number where it should be, that is at the very end of the array. By doing this, we are saving the CPU some crucial time. At the end of pass 2, we have our second largest number, that is 6, automatically where it should be. So clearly, our sequence of numbers has not been sorted even after pass 2. So we would again ask the CPU to go through another pass. Now again, we need not compare 5 and 6 since in the end of pass 2, 6 already is where it should be. So in general, in bubble sort, after pass n minus 1 numbers from the right can be skipped in the comparison process. For example, in pass 1, 0 elements were skipped. In pass 2, the last element was skipped. In pass 3, the last two elements were skipped. In pass 4, the last three elements will be skipped. By doing this, we are saving the CPU crucial time. Now, at this time, both you and I know that the sequence of numbers is sorted. But does the CPU know? No, it doesn't know that the numbers have been sorted. So we have to teach the CPU to detect when the sequence of numbers have been sorted. We do this by telling the CPU that if in a given pass not a single swap, or in other words not a single write operation is conducted, it can assume that the sequence of numbers is sorted. We will see this happen in the next pass. If we don't tell the CPU to stop, then the comparison process will keep on going back and forth like a typewriter. So in the next pass, the left number is always smaller than the right number, and hence we do not have any swap taking place. Thus, the CPU assumes that the sequence of numbers has been sorted and it stops. Now that we have seen the visualization of bubble sort, let us try to derive the algorithm. At the very core of bubble sort, we are basically comparing two consecutive numbers at a time and pushing the smaller one in front, and this action is repeated again and again, and it's important to note that it's consecutive numbers. Now we are going from the first memory location to the last memory location, and which we basically call a pass. So from the first memory location to the last memory location, we want to carry out the process of comparing two numbers at a time all the way and then pushing the smaller one in front. So this symbolizes a single pass. However, in bubble sort we have multiple passes. So until the sequence of numbers is sorted, we want to keep going on with the passes, and in each pass we want to carry out the process of comparing two numbers at a time, pushing the smaller one in front. Now we're going to use both C and Python to code it, and we're going to first start by initializing the header file. We do that by stdio.h and also define the int main function. In Python we do not have to initialize any sort of header file. So now we need some kind of a data structure in which we can store the sequence of numbers in consecutive memory locations. So in C we do that using a data type called array. We're going to define the data type of that array, which is going to be integers, and the name of that array, which is going to be, we can call that numbers, and initialize that using flower brackets with the numbers 7, 1, 5, 3, 2, 4, 6, basically any set of jumbled numbers. And this sequence of numbers arrays, we have to first define the size explicitly using square brackets. It's an array of length 7. So our sequence of numbers has 7 numbers in them, and then end the statement with a semicolon. In Python we do the same thing using lists. So we initialize that in square brackets instead of flower brackets, the same set of jumbled numbers, and we need not specify explicitly the size in Python. That's not needed. So now that we know the data structures and we have it ready, let us now try to execute the core functionality, that is comparing two numbers at a time and pushing the smaller one in front. We do that using the if keyword. So the if keyword helps us compare certain, it can help us compare numbers and then accordingly execute a block of code. So if the number represented by the left arrow or the left number in that comparison, right, we're going to use a variable x. X can be any number from 0 to 6 is greater than the right number, so that if the left number is represented by x, right number is going to be represented by x plus 1. So x here is basically an index, and in our arrays, in order to access the individual numbers in those memory locations, we use indexes. So indexes start from 0 and then go all the way till 6. So let's start with 0. So x will be 0 first, and it goes till 6, so that we can access the numbers in those arrays easily. So for now, we're going to compare whether 7 is greater than 1, because x is going to be 0 and 0 plus 1 is 1. So the left number is 7 and the right number is 1. So we're going to check, is the left number greater than the right number? If it is, we will start the swapping process. In the swapping process, we are going to store the right number in a temporary location. So let us declare the temporary variable. So in the temporary location, we will store it, and then we will write the left number into the right. Right, it is going to overwrite whatever is there with the left number. So we're going to store the left number in the right, and then whatever is there in temp, that is the value of the right number that we have temporarily stored, we will store that back into the left location. So this completes our swapping process using a temporary variable and then storing the left into the right, and then using the temp to store it back into the left so that we don't lose our numbers as we discussed in the previous video. So that's how we execute the if block. That now core functionality has been executed, where we are comparing the left number and the right number and pushing the smaller one in front. Now let's do that in Python. Similarly, we have the if keyword in Python, and before that we will first initialize our index. Indexes work in Python the same way they work in C. We will also initialize our temporary variable with none. So since we don't have a value for now, we will just call it none. In Python, when you don't have any initial value, you can just call it none. So if the left number represented by numbers of x, here x is the index, and the index is going to start from 0. So if x is greater than numbers of x plus 1, which is the right number, then we want to do the same thing. We want to use the temp variable to store the right number temporarily, then in the right location store the left number, and whatever there is there in the temp variable, now we will store it in the left number. So that completes the swapping process, and the core functionality here is completed. Now let's move a level up and ensure that this comparison process and swapping process is happening from the first memory location to the last memory location. Because as of now, it's only happening once. We want it to happen throughout the location. So we use the keyword while. So while is a loop. So the loop basically works as an iterative statement. So while x is less than 6, since x represents our index, and the index value can be anything from 0 to 5, right? And the reason we say 5 is because x represents the left number in our comparison pair, and the sixth one would be the right number. So because x is representing the left, we only go till 5, and we enclose our while in a flower bracket. So while x is less than 6, it will constantly do the comparison process starting from 0 all the way till the number 5, so that all the numbers are compared and the smaller ones are moved in front. So our second level is also carried out, and this helps us basically the x is equal to x plus 1. We have to say that in order for the loop to get incremented at each level, because initially x will be 0, then it has to be x is equal to 1, then x is equal to 2, then x is equal to 3. So in Python we also have the while loop, and again we're going to do the same thing. While x is less than 6, we want to execute this block of code, and in Python we don't have flower brackets, we do the indentation to represent the block, and we have to say x is equal to x plus 1 in order to move through the memory locations, and so that the loop increments. This is an increment statement, so that the loop increments from the first memory location to the last memory location. X can assume values from 0 all the way till 5, and accordingly x plus 1 will assume the right. Now we want to do this until the sequence is sorted. So how do we do that? If you remember, we in the previous video we said that if through a pass not a single swap or write operation is conducted, then we can assume that the array is sorted. So we'll keep a variable called swapped, and we'll set it as 1 for now, and then put another while loop. So as we discussed, we need another loop for n number of passes, because one pass is not enough. So while the variable swapped is equal to 1, swapped 1 means that a single swap, at least a single swap happened in that pass. So again we enclose the entire while into the third level, that is the until the sequence is swapped. Now the swapped variable, if the left number is greater than the right number, then the swapping mechanism happens. So inside the if body we can write swapped is equal to 1. That means at least one swapped happened. It's like a flag variable. But right now when we enter the loop, right, we have to ensure that before every pass our swapped variable is kept at 0, right? Because when we start our pass, our default swap value is 0. Only if a certain swap happens we can set it at 1. And if it does not become 1, then the while condition will not be satisfied, and it will break out of the outermost loop, and so we know that our numbers are sorted. But it's important for us to set swapped is equal to 0 before we start the pass, because the default value is 0. So this is the entire algorithm executed using C. In Python we can similarly do the same by putting an outer loop. Before that we can declare our swapped variable and say while swapped is 1, the same thing basically, we want to execute the inner loop, that is from the first memory location to the last memory location, and inside the if body we would set swapped is equal to 1, basically saying that yes, the swapping has been done, so we can set it as 1. And before we start the pass we'd have to set the swapped flag is 0, because in the beginning of the pass there's no swaps happened, so it has to be 0. And the same logic will work out in Python. Now that we have everything done, we also want to execute and print the we want to print our sorted array into the terminal on the console. We want to display it on the screen, right? We want to see what our CPU has done. So the way we do this is, after the outermost while loop we will declare another while loop by setting an index, another index as I, and saying that while I is less than 6, or this time we'll actually say 7, because we're going to go through all the 7. So until that's true, we're going to execute the printf statement. We're going to print each and every element of the array, and since it's a data type integer, we're going to specify %d, so numbers of I, that would individually print them in a single line. Now we would also have to add the increment I is equal to I plus 1, so that each time it increments from 0 all the way till 7, so that because it represents all the indexes in the sequence of numbers. Now we basically have to, there's one more thing we have to add, and that is x is equal to 0. So the outside the while loop, the second inner while loop, we have to set x is equal to 0, because every time we start the pass, our index value has to reset, because in the end of the pass it becomes 6. So it needs to reset to 0 in order for it to go through another pass. So not to forget the semicolon in the end. And we can now do the same thing in Python to execute our, actually in Python there's a simpler way to do it. Instead of going through the loop, we can simply say print list. So the list name is numbers, we can simply say print numbers. That's a feature in Python. So now we can go ahead and execute the program and see how it executes and sorts our program, sorts our numbers. We will do that by clicking on the play button here, and you can see that our numbers have been sorted 1 2 3 4 5 6 7, and we can go and check the Python code as well and see if that is executed, which it has. It returns the sorted list 1 2 3 4 5 6 7. So this is how we carry out bubble sort. In order to understand bubble sort better, you can download this animation software program that I have created using OpenGL and C++ with my friends Hajira, Zuha, and Abdul Rab. I will show you how to download it in the following steps. Open your browser and in the address bar paste the link given in the description. Then click on the button download. After that, within 5 seconds the download should start, and once the installer is downloaded, it will give you a prompt. Please click on keep. I can assure you that there is no malware in this program. Then you can run the installer and click on more info over here and click on run anyway. Then you have to click on yes and keep clicking next in the installer. It will automatically open the program when you finish, and press enter here and enter any bunch of 7 unsorted numbers, single digit numbers, and it will show you comparison by comparison, pass by pass, how bubble sort sorts a sequence of numbers. So with the number of comparison, the number of swaps, and the number of passes to, and it can help you better understand how bubble sort works, and also make you realize why it's called bubble sort, since the largest elements bubble to the top. Thank you for watching.